In this final screencast for Lecture 12 in Chem E 225 for Spring 2015, we're going to consider example 12.3, where we're using fminsearch and fsolve together to find the minimum of a cost function. Now, this system is the same as the example that we found in example 12.1, where we used fzero and fsolve to find the minimum. Now, in that case, we looked at fzero to find the zero of the derivative of the profits function. Now we're going to use fminsearch to simply just find the minimum of the negative of the profit function. Now note, we have to find the minimum of the negative of the profit function rather than the maximum of the profit function, because fminsearch only looks for minima and not maxima of functions. Okay, so again, what we have here is that we have an input flow rate of 4 species going into a condenser. Species C and D are going to be partially condensed into a liquid stream, and then whatever is left over is going to continue on as a vapor stream back as a recycle back to the reactor. So the way the previous example worked was as follows. So you have some initial guess for your minima, and you're going to call on fminsearch That fminsearch is going to then call on some function, f of x and y, as we saw in part B of the previous example. That function is going to spit f back out to fminsearch. And so what fminsearch is going to do is it's going to vary the two values of the two elements of capital Y, that would be x and little y, until it finds a minimum in the value of this function f, which is spit back out to it. And so fminsearch then will spit out what is y star, that is the minimizer of f. And so that's the way the solution strategy worked for example 12.2. But in this particular example now, what our solution strategy will be is the following. So we're going to take in an initial guess for the purity of our product, xc. That initial guess is going to go into fminsearch, which will then call on some function, which is minus the profits function, as a function of xc. That function will then spit back out to fminsearch the value of minus the profits function, and then hopefully fminsearch will then spit out what is xc star, or the maximizer of phi. Now, of course, the way this works is not quite this cleanly, because inside this function, you have to also call fsolve. So in this function is going to call on fsolve and give fsolve some y0 initial guess, right? And so this is solving for the value of n.l, the value of the temperature, etc., and other process variables that you don't know right away. And that fsolve is then going to call on some function that we've already written in the past, capital F of y. This is the same function that we saw in 12.1 and also in example 11.2. That function is going to spit back out to fsolve the value of capital F for the particular values of y. And then fsolve is going to vary all these different values of y until it finds a zero of the function f, and spit back out what is that y star, which is the root of f. Right? And so that's the way it worked. And before we had fzero instead of fminsearch up here, and we had the derivative of the profits function. And so if we draw a big box around this whole group here, this big group acts kind of to MATLAB, at least as far as fminsearch is concerned, as one big function where fminsearch is feeding into this box a value of xc and is getting back out of it a value of negative phi. And so that's the way that solution strategy is going to work. Now note again, just for your reference, this is what the profits function looks like as a function of xc, and it has some maximum here somewhere around xc equals 0.9 and about $70. Okay, so the way this function is going to look like, that fminsearch is going to call, is you have it's spitting out minus phi, or m phi is what I've called it here, and it's taking in xc, which is the main thing that it's going to vary in order to try to minimize the minus of phi. And also it has these extra parameters that you're passing to it as well. This is the initial guess for your for fsolve, and then the other physical constraints on the system like pressure and molar flow rates. Now inside this function it's going to define an f handle that's going to point to an inner function which is going to solve y for you. And so fsolve is going to go to that inner function and solve all the material balances and also Raoult's law equations to find your process variables y. Once we have these process variables y, we can calculate the energy balance to get what the required q dot is. Oops. And then once we have that, we can calculate the profits function phi and then take the minus of that m phi. And so in this outer function, it takes in these values of these parameters, specifically the first one being xc, which is a thing that fminsearch is going to vary. And through calling on fsolve, which then calls on this inner function, it finally eventually gets all the process variables calculated so you can calculate minus your profits function, which you're then going to spit back out to fminsearch. Now on the script side, it's going to look something like this, where what you have is you have an initial guess xc0 equals 0.9. You have an f handle which calls your outer function, and then you're going to make a call to fminsearch to that outer function, giving it the value of your initial guess, an options parameter, which is just a placeholder here by brackets, and then also these other parameters here, which you see as the other parameters that are in this function here. Finally, at the end, what fminsearch is going to spit out is it's going to spit out xc star, or the minimizer of the maximizer of phi, and it's going to spit out the value of minus phi, which then you can convert back into phi. Okay, so what does this look like on the MATLAB side? On the MATLAB side, what we have here is our outer function, which fminsearch is going to call directly. The first parameter of our outer function is this value of xc, which fminsearch is going to vary in hopes that it will find a value of m phi that a value of xc that will minimize m phi, right? And then here are the extra parameters to this outer function. Now this outer function, of course, is going to take a look at this inner function, which will solve all the other process variables in these nonlinear equations using fsolve to do it, unpacking what the values of that those process variables are, and then calculating the energy balance as we've done before, also in example 12.1 and 11.2. And finally, at the end of all of this, you calculate your profits function and give it the minus of the profits function that you spit back out as the output variable for this outer function. Now, I'm not going to show you what that inner function is because I've already shown it to you in a previous screencast, but what the script is going to look like, it's very similar to what we saw in the 12.1 script. But basically, we're defining our constants. We have our initial guesses for the process variables. We have our initial guess for xc, and we knew this was a good initial guess for xc. And the reason why we knew it is because we plotted it, right? So the graphical solution or the graphical method to find the maximum was useful in getting a good value for xc. So here's our f handle, then we call fminsearch. And fminsearch spits out not just the minimizer of m phi, but also the value of m phi that is the minimum, which is our maximum in our profits. Then what happens is that MATLAB, I've made the code for it to display these two things in MATLAB. So if we run this script, what we see is that the maximum of profits is about $70 per second, and this is obtained in a value of xc of this. Now I want to point out a couple other things here as we're winding down this example and this screencast. If I didn't know what a good initial guess for xc was, I might really screw things up. So let's go ahead and say, well, maybe this is my initial guess for xc. I don't know, maybe that's a good one. And then now if I run the script, what do I get in MATLAB? It's thinking about it. It's thinking about it. Uh-oh, there was a problem. There was a problem. It's giving me some warning output. And it says, well, you know what? Your maximum your profits is 10 to the 29. But that happens because you have a purity of negative 10 to the 10th, right? And so obviously something is going wrong here. What went wrong? Well, one thing that I know, at least from thinking about the physics of this problem, is that this value of xc is actually non-physical in my problem. Remember, the minimum value of xc that I could have in my problem is 0.75. And the reason for that was if I went ahead and I condensed all of the condensable, all of the moles of both of the condensable species, then we have a 3-to-1 ratio here. And so the 0.75 is the lowest purity I'll ever get in terms of what is my condensed value of the mole fraction of C, right? But even if I condense nothing, I also have a maximum value of xc that I'm going to run into, which was about 0.955 or 0.96 or something like that, which was the composition of the first droplet to condense at the dew point temperature, remember. So actually, the physicality of the system puts very strict limits on what values of xc might obtain in my system. So because of that, if I don't give it a good initial guess for xc, I might start off in some really non-physical realm and never recover. Or maybe if I give it even a physical value of xc, I might, because it might be a bad initial guess, I might accidentally jump to the non-physical realm and never be able to recover then either. Who knows, right? Another way you could handle this is if you have a function of one variable that you're trying to minimize, and you know the bounds on this one variable, then you can use a different function besides fminsearch. You can use a function called fminbound, and that function will accept almost exact same thing that fminsearch is going to accept, except for instead of an initial guess, here we accept two parameters in its place, a lower bound and an upper bound, and that will give it bounds within which it will try to minimize the function.